In this video, I'm going to talk about the energy of a simple pendulum. So let's remind ourselves of a diagram of a pendulum. We have some sort of ceiling. We have some sort of mass hanging from the wall with, I'm going to draw the axis as the dotted line, with some line that has a length which we'll call L. And then if we define a new quantity here, which is, let's say, the distance from the ball to the bottom of the ground is y. We define that as y. We define the distance from the axis to the ball as x. Well, then we draw some dotted line here. Well, then this distance right here, which I just draw, is equal to the length minus y. Well, you might say that, well, that's not logical because the length in this here, this length is different from this, right? But notice that the length, you can approximate it when the angle is small. So if you have something like this, there might be like a small angle, but the length of these two lines are pretty identical. So I'm just gonna approximate it here and then call this distance the length minus the L. Right? So by that conclusion, and we have a right triangle that has the bottom as x and the side as L minus y and the hypotenuse as L, right? So this can give us the equation, which is that the length squared is equal to length minus y squared plus x squared. If you expand this is going to give length squared minus 2, not 2x, but 2y length plus y squared plus x squared equal to length squared. And these two can cancel out. And then if you move this to the left side, it becomes positive. So this will become 2y times length is equal to y squared plus x. And then I'm going to do one more approximation here. As you can see, if let's say we have our simple pendulum, like have a really small angle, so something like this. This is badly drawn, but I'm going to zoom in. Say you have a really small angle, but this is the mass. You can see the y from the ball to the ground when the angle is really small. The y is like you can ignore it, neglect it, right? So in this case, we're gonna illuminate the y because the value is really small by approximating it. I know this sounds sketchy because it was sounding really sketchy when I first learned it as well, but just keep along with me. So if we illuminate y because the value is too small, this becomes 2y times the length is equal to x squared, or y is equal to x squared divided by 2 times the length, I think. Yep. Right? So we have obtained the y. Now, as you know, the potential energy of this thing, let's say we have a pendulum right here that oscillates from the left to the right, like it has some distance, which we call y, when it rises, right? So the potential energy or the work done at that case is force times the y, right? Because the energy or the work is defined as force times the distance, and the distance in this case is the y. So our force right here is obviously going to be mg, and our y right here, as we already got this relationship, is going to be x squared divided by 2 times the length, right? So this is going to be our potential energy for our spring, because think about it, like when the pendulum oscillates like this. I'm going to redraw the diagram. And then it goes here, right? At this point, I'm going to highlight it with red. At this point, the kinetic energy is the maximum, and then it starts decreasing as you go up, and the potential energy start increasing. So this right here kind of is like it's like how much the potential energy is for this thing, right? Because it's rising. So if this is the potential energy, we know that the energy for the total the total energy for the formula, the energy for the formula for the total energy is equal to the kinetic energy plus the potential energy. And the kinetic energy in this case can be 1/2 mv squared, of course, as always, plus our potential energy, which we just did here, is going to be 1/2 mg x squared divided by L. Yep. Right? And then remember at the turning point of the motion, which is if we draw the diagram again, okay, so it's gonna be like this, m goes like this, goes back and forth, right? So at this point of the motion, x is gonna be equal to, let's call this amplitude a. So at this point where x is equal to a, which is when the maximum, when the potential energy is the maximum, right? Because when you release the pendulum from a certain height, it has zero velocity. It is not moving, and it has the highest potential energy the moment you release it. So at the highest point, so at this point, which we call A, it has no velocity, but it has the highest potential energy. So that kind of amplitude defines the total energy of the system, because it's not going to be like if you release it from, let's say, a height of 2 centimeter, then it oscillates back into like 3 centimeter, because it doesn't work that way, because it violates the conservation of energy. So at that point, like the initial position of the pendulum really defines the total energy of the system. So in this case, our total energy is going to be, if our velocity is going to be equal to 0, so this is going to be times 0 squared, obviously, plus 1 over 2 mg. I'll replace x squared by a, because a is our initial position, over L. So our total energy in the system is basically 1 over 2 times mg a squared divided by L. That is going to be our total energy in the system. So from conservation of energy, we can keep going with this equation and see what conclusion we can draw. So the next step is we know that this is the total energy. So let's write it out. So the total energy is 1 over 2 times mg a squared, where a is the maximum amplitude where you started, divided by length is equal to 1 over 2 mv squared plus what is it? 1 over 2 mg x squared divided by length, right? So now I'm gonna, for the sake of the convenience, I'm gonna cancel out the 1 over 2s. So they all have 1 over 2, so we can cancel all of them out by dividing them. So now we're left with this, and this. And then now what we could do is that we could use it to obtain an expression for the velocity v and the displacement x. So we do that by, well, first isolating velocity v, of course. So if you want to isolate v right here, so what do you do? Well, you move this to the left side. So this is going to be mg a squared divided by length minus mg x squared divided by length is equal to mv squared for now, right? So you learned this in elementary school. This is going to be length. It's going to be mg a squared minus mg x squared divided by the length. It's going to be equal to mv squared. And then now if you want to isolate v, you move the m to this side, to the bottom of this, and then so this is going to become mg a squared minus mg x squared divided by length times m, and the m's cancels it out. This is going to be if you take g out of it as well, right, because they both have g, you can take g out of it. So this is going to be a squared minus x squared divided by length is going to be equal to v. And then if you just square v squared of, so if you want to if you want v, you need to square root this whole thing. So this whole thing just becomes square root of g of a squared minus x squared divided by L. So this is our v, right? So now we obtain expression for v. Now, as you also know that what v essentially is equal to the change in the displacement. So it's equal to dx over dt. So by that logic, if we make that equal to it, so it's something like this. And then you know that one of the other basic fact of the square root and the rules of it is that this can be written as square root of g over L times square root of a squared minus x squared. So this is equal to dx dt. So now if we move dt to the right side, so if we move this to here and we move this to the bottom of this gives us dx over square root of a squared minus x squared is equal to square root of g over length times dt. And now you integrate this whole thing. So let's do that. So let's add the integration sign. We integrate this whole thing. Well, for the right side, it's pretty simple because we just take the constant amount as g and l are both constant. They're not like a variable that changes. So we take this out, and then this gives us dt. This is going to give us, if you integrate the dt of u, obviously it's going to give you t, and then you have some kind of constant. I'm going to call c for now. And then the left hand side is kind of complicated, but I already did the integration already by using the substitution. You can use the substitution and define x as a sine of theta. So by doing that, what you're going to obtain is you're going to obtain sine. So actually, let's write it here. You're going to obtain sine -1 x over a is equal to this thing. So you obtain this by integrating the both part of it. So now, well, if you want to get rid of the -1 for the sine, you do something like this. You just move this whole thing inside. So this becomes plus c is equal to x over a, or x is equal to a sine theta, square root of g over l plus, let's call this c, the phase angle. So now you have, if you look at this and compare to the expression that we had before for simple harmonic motion, this is very similar, because as you can see here, we have some a, which is remember our a is the starting point, which is how high have you lifted the pendulum, what is like the highest or the maximum starting point. And we have a sine, which is a periodic function as well. So we have our x, which is the displacement, of course. So now we have successfully attained an expression for the displacement equation for a simple pendulum. Yeah, and I kind of want to go back and look at this equation that we have here. Well, in this equation, this one, I'm going to move this whole thing out. Actually, I'm going to do this. I'm going to move this whole thing out like this. This is pretty important, because what this relates is that this is the velocity of the pendulum, and then our variable here is x. So what this actually tells you is that it actually describes how the velocity changes with displacement x in the simple harmonic motion, right? So like as the x changes, and then you have g, a, length as fixed values. As x changes, how does that affect the velocity of the simple pendulum? So that's also a pretty useful equation if you want to solve some other question. Yeah. So this will basically be a video on the energy of a simple pendulum and a simple harmonic expression for the simple pendulum as well.